Here we're showing the mission that we programmed into our drone. The drone's mission is to take off at node T, travel to a 5-meter hover above node L, then land at node L. If it detects the landing tag, it will then pursue the landing tag for its final landing. The trajectory in red, which begins at T and then turns back, is due to the tag tracking, where we dragged the tag back toward the takeoff location. The large red arrow is the indicator of the vehicle's position when this screenshot was taken, the final point of the flight. Spool up is when we get the propellers started, because they all need to be running before the vehicle can fly. Auto mode is when the vehicle is flying autonomously and following GPS coordinates through its mission. It's now going to the 5-meter hover, where it will wait for 3 seconds while I begin to pull the tag. Then it will enter landing mode. The vehicle's now entered landing mode and is descending toward the tag. We can see here that it slightly overshoots where it is expecting the tag to be, and then corrects its positioning. And here, it is spot on above the tag until the last quarter meter of landing. The reason it loses tracking in the last quarter meter is because the 16.5 centimeter large tag is larger than the entire camera field of view at that height, and so it can no longer detect the tag because the tag is filling the entire field of view. Thanks for watching our presentation. Leave a note in the comments if you have any questions, and have a good day. Good morning, ladies and gentlemen. Welcome to the presentation of VisHawk RF Silent Drone Navigation. I'm Matthew Dupree, the student team lead, and I'm here with...
Hi, I'm Shihan Liu. I'm responsible for data analysis.
Hi, I'm In Chao. I worked on printed circuit board design.
And the project roles got a little more mixed up than that. We were all working on different parts of the project all together at different stages. So first, an overview. What exactly am I talking about when I say RF silent and drone navigation, that kind of thing? The basic goals of the project are we want to lift off from a boat that is underway at sea, or not underway, we just want to lift off from a boat at sea, land on another boat at sea, and that is a very tricky challenge because landing on a boat at sea means we have a limited size landing area. We have a moving landing area because the tides and the waves are going to push the boat around. And if we miss that landing area, our hardware ends up in the water, and wet hardware is usually non-functional hardware. We also want our project to be RF silent. That is, no radio communication. There's no way to locate the drone in space because there's no pilot with a remote control maneuvering it. There is no landing beacon that's going to tell the drone exactly where the deck of the ship is. And there's no external processing to send the video footage out to say, okay, yeah, the ship is there. Everything we do has to be on board the drone, which means we need to identify the landing target via some kind of computer vision on the energy budget of what the drone's hardware can handle. Just to formalize that problem a little bit more, we've got 2 boats, a lot of water between them, and a drone that needs to lift off from one ship and land on another. We also want to do that without talking to anybody. We can't have a pilot on the ship. We can't have a pilot in Nevada. We can't have a landing beacon that would mark out the location of the ship. What we need is something entirely visual that's hard for other computers to pick up that we can use to identify the ship we want to land on. And so we've focused on the latter half of this problem, trying to get the drone down onto a target ship's deck without communicating with that ship and without communicating with the outside world. And so we've assumed that until we can get within being able to see the ship's deck, we can use GPS to navigate to a location we expect the boat to be. Here's the block diagram of our project, and Ying Chao is going to break it down a bit more.
I will introduce these blocks in details. There are 2 processors in our system. The main processor is Raspberry Pi, which handles the computer vision part. A Pi camera is connected in parallel with the Raspberry Pi in order to detect the tag. There used to be a servo attached to the camera, which allows us to get up to 180 degrees of view, but we had trouble with vision transformation. with a moving servo, we need to configure different sets of parameters at different angles. So we decided to use only a fixed down-facing camera for detection, and that's enough for searching the tag when the drone is up in the air. To control the Raspberry Pi, we SSH log into the system using our own computers and type in the launch command. The coprocessor is VisHawk, which interfaces with the Raspberry Pi using UART transmitter and the receiver. It ensures drone stability in flight. Motors make the propeller spin. Here we are using three-phase motors. Comparing with single-phase motors, three-phase motors are more commonly used in industry, since their power is over 150% greater than that of a single-phase motor, and less noisy. Finally, all the black arrows here represent the power flow. A 4S LiPo battery is the only power source. It supplies the flight controller and the motors. The Raspberry Pi can only support 5 volt input voltage, so a voltage regulator is needed to convert the high voltage to 5 volts to supply the Pi.
Next, we're going to break down the hardware layout on the chassis. Shihan?
Yes, so we will introduce our design layer by layer. On the top of the drone, we have GPS, flight controller, and telemetry radio. In the middle part, we have a companion computer and a mounted camera. At the bottom, we have a 4S LiPo battery. For the flight controller, we choose to use VisHawk 2.4.8 because it comes with a GPS antenna and supported by quadricopter APM firmware, which contains precision landing mode that is what we needed for landing detection. And we included an anti-vibration pad stick under the flight controller to ensure stable flight. We also mounted a GPS block for achieving drone's longitude and latitude data without RF communication. This module will not be used after a landing target detected. The telemetry radio is mounted on one of the 4 branches for balancing. It is used for broadcasting information and displaying in ground control station during our flying experiments, and we can take this part off in the real flight.
The middle layer consists of a companion computer and a camera. The component we chose for the companion computer is Raspberry Pi 3B+. It's the final revision in the Raspberry Pi 3 range. Comparing with other models in 3 range, it has faster Ethernet. We can log into the Pi when we are on the same network. Its job is to perform computer vision tasks to identify the target and communicate target transform to the flight controller unit. Then here is the bottom view of our drone. We mounted the camera on a 3D printed board. It's Raspberry Pi camera module V2. It's capable of taking photographs of high resolution. We use this to detect April text in a lower resolution because we want to get higher frame rate. But due to Raspberry Pi processing limitation, it can only process about 10 frames per second. So that's what 10 FPS here means. At bottom, there is a 4S LiPo battery. It's the only power source for our whole system.
Okay. And now we're going to talk a bit about the printed circuit board that we use to regulate power going to the Raspberry Pi.
This is the schematic of our PCB. It functions as a voltage regulator to convert the input voltage from 14 to 22 volts to 5 volt output voltage. We also put a diode after the input voltage in order to prevent reverse current. Because during testing, when we powered the Raspberry Pi by USB, we noticed that the VisHawk was also lighted up. So a diode can prevent this from happening. On the left, this is the PCB board design made with Eagle software. Then we have the final product of our 2-layer PCB. It's 45 by 59 millimeter large. The inductor and the diode occupy most of the space. We also put a lot of drill holes for thermal dissipation.
And now I'm going to break down the software stack that we use to make the drone fly to the areas we wanted to go to. First, and most critically, is the system we use to identify the landing location. We're using the April Tag 3 visual fiducial developed by the University of Michigan. The tag is represented by a whole bunch of little bits, the white and black squares you can see. And so there is a wide space of tags that one can generate. And only the target tag is going to be detected by the April Tag 3 library. So the system has an extremely low false positive rate. It locates rectangles in the environment. It reduces down the code by a Hamming scheme compression algorithm, error correction algorithm, sorry, and then determines whether that code is the specific tag we're looking for. And using all of these stages in hours and hours of testing, we've only had about 32 misdetected tags, and every one of those tags had a different ID from the one we were intending to land on at the time, meaning they did not affect our system whatsoever. With the current onboard processing of the Raspberry Pi, we are able to read in a 640 by 480 resolution, which at a 5-meter altitude gives us a 5-meter deep by 6.7 meter wide box below the vehicle, in which we are searching for this 16.5 centimeter square tag. If we had more processing power, we could read higher resolutions and get significantly better ability to recognize the tag at distance, higher search altitudes. At the moment, though, the highest search altitude we're able to detect the tag at is 7.2 meters. Next, the flight control unit on board the craft also needs a piece of software telling it how to keep the drone stable. Our first choice was the PX4 Autopilot, which is a beginner-friendly OS with lots of useful debugging features, such as the Mavlink shell that lets us run debugging commands on the PixHawk itself over the Mavlink standard, so from the Raspberry Pi. However, PixHawk would only accept coordinate frames in what's called local northeast down, meaning a frame defined when the drone takes off, where X is north, east is Y, and down is Z. And unfortunately, we're trying to lift off from a moving boat and land on a moving boat. So that local northeast down frame doesn't work for our use case because the landing target will be moving around. And so we had to move to a different OS. Second, we chose Arducopter Multicopter Autopilot from the ArduPilot series of autopilots. This is much more heavily used in industry, has many more advanced features and configurations, but it is slightly older, and its code base is basically spaghetti. There's all sorts of dependencies every which way. It's also missing useful debugging tools like the Mavlink shell, and we ended up having to use a post-hoc debugging process I'll go into in a moment. The companion OS, that is the OS on the companion computer, our Raspberry Pi 3B+, is Ubiquiti Robotics' Ubuntu Mate 18.04 with ROS Kinetic. Ubiquiti Robotics is providing this distro of Ubuntu free of charge with open source, and so there's no legal liabilities relating to it. ROS, the robot operating system, is an inter-process communication scheme, allowing us to spread the processing of our vision information across all the cores of the Raspberry Pi to get the maximum use out of the Raspberry Pi hardware. It also has a number of logging tools so that we can read the inter-process communication messages and analyze the behavior of the drone after a flight. This is the processing pipeline we built inside of ROS, and I'll break it down. First, we read the Raspberry Pi images from the Raspberry Pi camera using RaspBiCam node. This node initially published images in a way that was unsynchronized with the camera info state, and we had to rewrite a large portion of the node to produce the images in an unencoded format April Tag ROS would accept, and with the synchronization information, the camera state information arriving synchronized. April Tag ROS is a wrapper around the April Tag 3 library that extracts the location of the tag relative to the camera. It then produces those tag positions, which travel to Vision to Mavros. Vision to Mavros is a small wrapper package that just translates the vision tags from the space of I'm the camera, here is the tag, to this is the tag, this is the origin of our space, the drone is here. And we send those targeting positions of the drone to Mavros, which is a wrapper for the Mavlink communication standard. Mavlink is sent over UART to communicate with the VisHawk, and it is a common autonomous drone component communication system. And then Mavros sends the data to the flight control unit. At every stage in this process, we pulled out logging data that we reformatted for vsub.py, a custom visualizer we made to make sure that all of the transformations were going correctly, because we had a number of issues along the way. But with the switch to ArduPilot OS, we no longer had the Mavlink shell on board the vehicle, and so we ended up having to read the logs in a post-hoc manner using MavExplorer, because we could only get data flash logs after a flight or a test. Now Shihan will talk a little bit about more about the transformations and debugging tools and all of that process.
So right now we are focusing on extracting location data of the drone relative to the camera position. For the ROS operating system, there are several command line tools. ROS topic echo is one of them. We use this tool to listen to the topic TF, which is subscribed by Vision to Mavros node. And this node would help convert angle and distance according to east-north-up conversion with user input rho, pitch, yaw, and gamma angles. We do one more transformation into a northeast-down frame, which is used by our flight controller. After the flight controller gets the data, we use the Mavlink share, which is used for running commands and displays the output. We at this point could able to see what the message contents received for VisHawk. Simply displaying the position data is not enough to compare the consistency information between our companion computer and flight controller. So we convert the Mavlink output and write into a YAML document stream. Meanwhile, we grabbed the display data source from Vision post from the ROS node and transferred to local computer as sources for our vsub.py debug program via SSH pipeline. With these two sources, we could better visualize them onto a Matplotlib 3D plot for more straightforward understanding.
Thank you. So all that was a little complicated. Let's just see it in action. Here we've got a demo video of the craft doing a flight. And I'm not seeing the interface for playing it. Kyle? Oh, shucks, there it was. So our mission is to take off at node T and land at, and we lost the slide. The mission is taking off at node T and landing at node L. The red trajectory on the map is caused by tracking of the tag and pursuing the tag, which we were dragging back past the takeoff location, meaning it was tracking a moving tag on the ground that happened to pass through the region it was expecting to land in. I'll stop moving the mouse so you can start the video and we'll just run straight through. Sorry, Kyle. Spool up. Spool up is when we're getting the motor started, because unless all four are running, the vehicle will flip over. Auto mode is automatically determining the GPS coordinates to travel to and just following a pre-programmed mission. It will go to a 5-meter hover and then wait there for 3 seconds. I start moving the tag when it reaches that hover. It then enters landing mode and is now pursuing to catch up with the tag. Here, it slightly overshoots the actual location of the tag and corrects its positioning, and then continues its descent. Only in the last quarter meter does it lose sight of the tag. It loses sight of the tag because the tag at that height versus the vehicle is such that the entire camera field of view is taken up by the tag. And unless the camera can see the whole tag, it will not register the tag and make any detections. This project has had a lot of challenges along the way, and we'd like to extend our special thanks to NAVSEA for funding our project research, Alan Yeager for being our contact with NAVSEA, Dr. Yogande Iskupali for running the UCSB computer engineering capstone this year, Aditya and Kyle, our 2 TAs, for helping us so much in office hours, and Qualcomm, NAVSEA, and UC Santa Barbara Engineering all together for funding the capstone program. We'd also like to thank all of you for listening. Anyone have any questions?
How many times did you guys crash your drone?
We had at least 8, 10 flight attempts that ended with a harder than expected landing.
Hey guys, good job. Knowing what you know now, what would you have done differently if you were starting over again?
Start with the APM firmware, pick a flight controller that integrated with the ESCs directly. So putting the ESCs on would have been easier. And then, I mean, honestly, there's so many little details in the whole process that it's difficult to go over everything we could have changed. Yingqiao, Shihan, any other specific ideas? A lot of our problems in the project came from just not knowing certain configuration options existed and them being in a state that wasn't conducive to our vehicle operating in this manner. All sorts of rotation transformations and parts of the Kalman filtering. The vehicle itself, the reason we needed the spool up extended is our motors take a moment longer to start up than we realize. And so some of our crashes were related to it not starting those motors correctly. On top of that, there were motor spin direction configurations that we had to deal with, and that delayed almost our entire first quarter. It's just so many bumps and things to learn along the way. And if we started over now, we could definitely make all the progress we've made in a quarter.
Well,
that's
a challenging
because
problem.
we made all that progress. Yeah.
Yeah, it's a challenging problem. A lot of people are trying to solve in a lot of different elements. So good job. Hope you guys learned something, had a little bit of fun along the way.